In this example, we are being asked to determine the inclination angle theta of this brace if it's on the verge of slipping at point A. So let's take a look at what we have here. We have this diagonal brace, let's call it AB, and it's on the verge of slipping here at point A. And the inclination angle that the brace is making with a horizontal reference axis is theta. And we have this force of 180 pounds hanging like so. And that's measured a horizontal distance of 3 feet away from this left-hand side of the system, okay? So we're also told that the coefficient of static friction at point A is mu sub s equal to 0.4. And point B is a smooth surface. So whenever you see the term smooth surface, you can assume that that is frictionless. You have no friction developing there. You only have a normal force developed at a smooth surface. And then the brace is 10 feet long. So the 10 feet dimension is this diagonal length right here. The physical length of the brace AB is 10 feet long. So let's go ahead and begin our solution with a free body diagram of this system. So under solution, we're going to say free body diagram of the entire system. So just to keep with our color coordination, we're going to have this diagonal brace right here, AB. And let's start with B first because that's kind of easy. It said B is a smooth contact surface. And if you remember from chapter 5, a smooth contact surface only has a normal force develop at the point of contact perpendicular to the surface it's resting on. So that's why our normal force in B is completely horizontal like so. Down at A, however, you do have this friction force that can develop, and that's obvious because you were given a coefficient of friction of 0.4 at point A. So at point A, you're going to have two forces that develop. You're going to have a normal force at A. So again, that's going to be in A, and that's perpendicular to the point of contact at A. And then you're going to have a friction force develop at A. And so we can go ahead and draw that friction force maybe like this. And we'll call this F sub A. Okay. And this is a free body diagram, so you need to put all of your known and unknown values here. So we also don't know this angle theta. In fact, that's what we're being asked to calculate. And we know something is here. We know that we have 180 pounds, and that is going to be right here, 180 pounds. And we know that this is a distance of 3 feet away from that wall on the left side right here. So this is our free body diagram. And when you first look at the, don't forget about the 10 feet. Let's go ahead and put that on there. So this diagonal dimension right here, which is the length of that segment, is 10 feet. So if you look at this, you may be looking at this, you may be saying, wow, I've got 4 unknowns. I have an NB that I don't know. I have NA that I don't know. I don't know FA, and I definitely don't know theta because that's ultimately what we're being asked to compute. So the first thing we can do here, which is pretty obvious, is we're gonna set up our relationship with our coefficient of friction. So if you remember, our friction properties tell us that our friction force Fa is equal to mu sub s times the normal force at that same point, okay? And so we can say that this is 0.4 times NA. So that's going to be one of our relationships. And notice we have 4 unknowns. So we're going to ultimately need 4 equations or 4 relationships to tackle this problem. So our first relationship that we're utilizing is the definition of static friction. Friction force equals coefficient of friction times the normal force at that point. Now, what other 3 relationships can we use? Well, This is a rigid body. This is a two-dimensional rigid body. So our next three equations, giving us a total of four equations, will be our three equilibrium equations. And so finally, from the three equilibrium equations and this friction relationship, we're going to have four equations that we can use to solve for the four unknowns. But, most notably, what we're mostly interested in is the theta eventually. So let's go ahead and set these up. How about we say equation number 2 is going to be our force equilibrium equation for x components. So sum of the forces in the x direction equals 0. So just look at your free body diagram. We'll say NB plus FA equals 0. Now remember, these forces are all unknown right now. That means we had to assume these directions. So just like way back in earlier problems in this class, we assume the directions of the unknown forces. We know FA is horizontal. I'm just going to assume it's pointing to the right. I know NA is vertical. I'm going to assume it's pointing up. I know NB is horizontal. I'm going to assume it's pointing to the right. If I do some calculations and something comes out negative, then it is in fact pointing in the opposite direction. So all of these static rules that we've learned earlier in the class still govern. All right, so we have this relationship. Let's move on. How about we say sum of the forces in the y direction equals 0. So our next equation number 3, will be sum of the forces in the y direction equals 0. Call things pointing up positive. So here, what do we have in the y direction? Well, we have a minus 180 pounds plus NA equals 0. So this is pretty obvious. We can directly look at this and we say, well, obviously NA must be 180 pounds reacting upwards. Okay, so actually that's one of our easy to deal with unknowns we solve for directly. And then our fourth equilibrium equation, well, it's actually our third equilibrium equation, but it's our fourth equation total, will be the sum of the moments about a point equals 0. Counterclockwise positive. You can sum moments about any point. I would say let's go ahead and sum moments about point B. And the reason why is you already, very conveniently have this 3-foot dimension that's a perpendicular distance from the 180 pounds to point B. So summing moments about point B would be the most convenient in this problem. So summing moments about point B and looking at this free body diagram, we're going to have NA times 10 feet times the cosine of theta. And I'm getting that because, 10 feet cosine theta will give me this perpendicular distance right here. Okay, remember the 10 feet is this hypotenuse. So if you say hypotenuse times cosine of theta, you'll get a horizontal component. So that's where the 10 cosine theta comes from. And then next component, we're going to say plus FA times 10 feet times the sine of theta. Okay, now again, where does that come from? Well, we have FA here and we need its perpendicular distance up to point B, so we need this vertical distance, and to get this vertical distance we say the 10-foot hypotenuse times the sine of this interior angle gets you the vertical distance. And again, watch our directions here. NA is causing a counterclockwise moment about point B, and FA is also causing a counterclockwise moment about point B as well. So both of these are positive. And then finally, we're going to have minus 180 pounds conveniently times its 3-foot perpendicular distance, all equaling 0. So here we go. We've got all of these equations set up, and we have them related properly, so we can start solving for things. Well, we already solved for NA is 180 pounds. Now, how about we go ahead and solve for FA, right? So let's say from equation 2, we can say FA equals negative NB. Okay, and then we also can say from equation 1, we can say FA equals 0.4 times NA. And we already got NA is 180 pounds, so we'll say 0.4 times 180 pounds. And that gives us, I believe, 72 pounds. So now we have FA, and we can go ahead and get NB as well. So we can say NB equals negative 72 pounds, okay? And so if NB is negative 72 pounds, that just means that it's going to point in the opposite direction that we assumed, which would be to the left. So we can end up saying equals 72 pounds pointing to the left there, okay? So looking back at our free body diagram, if you want to, we can check some things off. We got NB just now, we got NA, we got FA. So the only thing we're missing right now is theta, okay? Is theta. So where can we get theta? Well, if you notice, theta is built into this moment equilibrium equation. So what we can do is substitute things into the moment equilibrium equation and solve for theta. So let's do that one step at a time. I'm going to say now, let's change colors again. Maybe let's do, how about we do purple? We're going to say from equation 4, we already got NA is 180 pounds pointing up like we assumed. So we'd say 180 pounds times 10 feet times cosine theta. And then we just got FA is 72 pounds, so plus 72 pounds times 10 feet times sine of theta. And then 180 times 3 is 540, so we'll say minus 540 pound-feet equals 0. So we can do a little bit of simplifying here. We'll get 1,800 pound-feet times cosine theta, and then we'll get plus 720 pound-feet times sine of theta equals 540 pound-feet. And so here this is a very kind of a somewhat tedious equation to solve for theta, because notice you got theta trapped inside a cosine and a sine. So what I ended up doing was I said use num solve in TI-36X Pro, and this num solve is above the sine button. It's in blue on that calculator, and so when you do that, you'll solve for theta, and I get theta equals 52.5 degrees. And so that's the answer that the problem is asking for. You also got a lot of good other information out of here. We got all of this good information about all these forces. So the problem could just as well have asked for all of these normal and friction forces, and we got them. But the problem just so happened to only ask for theta. But notice we had to move through and get those forces in order to finally solve for that theta value. So that concludes this example.